A few of you have informed me that the warm-up in the first Smartwork homework from Chapter 10 has some kind of funky questions that we didn't go over in lecture. And so I'm going to work a couple of examples of those to help you get through the warm-up. The warm-up contains questions that I don't have a choice over, which is why I try to minimize the overall percentage importance of the warm-up. So when it does have questions that we haven't gone over, I will try to do this. But anyway, we have talked about total internal energy being a combination, or change in energy, a combination of heat or work done. And so we've talked a lot about heat, which for our purposes is the same in change in enthalpy. We haven't talked much about work. So I'm going to do a couple of those quick examples. They're not hard. So work is also defined, and that's where these calculations come in that you're being asked to do in Smartwork, as pressure times, minus pressure times change in volume. And so the only time one of our systems in chemistry can do work, there has to be a gas present, okay? Because gases are the only thing that can change their volume significantly, and we need a change in volume in order to have work done to or on a system. So let's look at the example they give us. You can also look in your textbook. This is pulled right out of your textbook in Chapter 10. And so here is the question. It's not a chemical reaction, but they're blowing up a bunch of helium balloons, and there are 100 balloons. Each of them can hold 4.8 liters of a gas, and how much work is done by the helium. So we're going to think of the helium as our system, right, and the atmosphere as our surroundings. So the pressure is just whatever they tell you atmospheric pressure is, and that doesn't change. So here they told us, okay, atmospheric pressure is 1.01. That's very common atmospheric pressure. And so now we have to find the change in the volume. So let's look at how they did it in this example in your book, and then I will work out one that I think is similar, a little bit more similar to what you're being asked to do in Smartwork warm-up. All right, so here is the pressure. Don't forget the minus sign. And minus, remember, anytime you have work or heat that has a minus sign, it means that the system, which in this case is our helium, is doing work on the surroundings. Okay, and what that means is that the pressure of our system is increasing. Okay, so we're blowing up the balloons, right? We are increasing the pressure of our system. So you can think of the helium that we're putting in the balloons as exerting pressure on our atmosphere. They're doing work on our atmosphere. Now, if we have a system and it shrinks, the volume decreases, that means that the atmosphere is doing work on our system, and that would have a positive sign. So the original volume is 0 because we didn't have anything, right? Okay, so the final volume, which is what we're trying to find out once all those balloons are inflated, there are 4.8 liters for each balloon. There are 100 balloons. And so that tells us that there are, if I can multiply, 480 liters, and that is our final volume. And so at this point, let's see, I'm just doing it stepwise here for you. So 480 liters times minus 1.01. Okay, so I'm putting that in my calculator real quick. So work can be in the units of liters times atmosphere, but in this case, they asked you to put the units in joules or kilojoules. So you may want to jot down this conversion factor. It takes units of liters atmosphere and converts them to joules. So hold on just a minute. Let me punch this in and see what it would be in liters atmosphere. All right, so in liters atmosphere, we have 484.8 liter atmosphere of work. But since the problem asks for it to be in kilojoules, we are then going to convert that liters atmosphere to kilojoules, joules and then kilojoules by using the conversion factor of 101.325 joules per 1 liter atmosphere. All right, so the liter atmosphere cancel, and you get minus 4.9 times 10 to the 4th joules. Okay. Pay attention to Sig Figs, especially in Smartwork. Notice 1.01 atmosphere has 3 Sig Figs, but 4.8 liters only has 2 Sig Figs, so your final answer can only have 2 Sig Figs. All right, so this is a sample problem that somebody sent me a screenshot directly from the Smartwork warm-up for the first Smartwork assignment in the week 1 folder in D2L. And everybody gets slightly different numbers, but a similar problem, so you should be able to work yours out using this as a model. So we have a chemical reaction here, and they asked us for the amount of work done. So I'm going to rewrite the formula for you. And they gave us the atmosphere, the external atmosphere. They simply said was 1 atmosphere, which is nice and handy. So our job is to find the change in volume that occurs when this chemical reaction occurs. So the chemical reaction is our system. Now, remember that work by a chemical system can only be done if there is a gas present. A gas is the only thing that can change its volume, and that's what creates work. So look at the states of matter in this reaction that they give you. Every reactant is a solid, okay, which means originally there's no change in volume, okay? So the original volume contributed by this system is 0. So all we have to do is find the final volume, that's the volume of the products, and we'll have the change in volume at that point. So only look at the products that are gases. So potassium sulfide is a solid, but nitrogen and carbon dioxide are gases. So we have to figure out the quantity of these 2 gases and then convert that quantity to a volume to see how much volume was generated. So this is a tricky problem. They want you to do stoichiometry, which we learned last semester, in addition to using the work formula. So let's go ahead and do our stoichiometry first. Just typical, this is good practice anyway, even though I'm sure you're all rolling your eyes at this problem, and I kind of am too. All right, so 2.55 grams of potassium nitrate. The molar mass of potassium nitrate is 101.1032. All right, and so now that we have it in moles of potassium nitrate, we need to look at the mole ratio of our balanced equation because we're trying to get to nitrogen and carbon dioxide. And I see that according to the balanced equation, for every 2 moles of KNO3, I make 1 mole of nitrogen. And so how many moles of nitrogen do I have? All right. So I know how many moles of nitrogen gas I've generated. Now let's do the same thing and figure out how many moles of CO2 I've generated. I'm going to go through the same process, but I'm going to use the mole ratio for carbon dioxide now. Alrighty, so mole ratio for every 2 moles of KNO3, I make 3 moles of carbon dioxide. And so the moles of carbon dioxide this system has generated is 0.0378. All right, so we have moles of the two gases made. What do we do with that? We have to get to liters, okay, in order to get how much the volume of gas that's been generated. So how do we get from moles to liter? Well, if you reread the problem again, they give us the density of each of these two gases, and that's what we're going to use as a conversion factor. So the density of the nitrogen gas is 1.165 grams per liter, and density of the carbon dioxide gas is 1.830 grams per liter. All right, so in order to get to liters, we need grams of each of these gases, and so far we have moles. So we're going to go ahead and do another conversion between moles and grams. Now, at this point, your eyes may be rolling in the back of your head saying, this is like really hard. So let me assure you, I've just decided while I'm working it, this type of question will not be on my regular first exam, but I'm thinking it might be a really good bonus question on the first exam for those of you, and that'll encourage those of you to kind of do the extra work to understand what you're doing. And it's also very good practice. I will tell you, this is very typical for Chem 1212 as far as the level of intensity of the problems. I think because they're combining so many different things we've learned all together. So practice tons of problems. Anyway, so I'm going to go ahead and take the mole values that we have so far for nitrogen and carbon dioxide and convert them to grams and then liters. So here's how much we found of nitrogen, and the molar mass of nitrogen gas N2 is 28.02. All right, so that would give me grams of N2. I'm going to do kind of a long run-on conversion. So I'm going to go ahead and use let me do it stepwise for now in case I don't want to lose anybody. So I'm going to go ahead and write out the grams that I have of nitrogen. And it would be 0.353 grams of nitrogen. Okay, so now I'm going to use the density of nitrogen as a conversion factor to get to liters. I have to make sure grams is on the bottom, so I've got to flip it upside down so that grams cancels out. And when I go ahead and do that, 0.353 divided by 1.165, I get that the total liters I have of nitrogen gas is 0.303 liters. All right, now we have to do the same thing for CO2. So we had 0.0378 moles of CO2 have been formed. Molar mass of CO2 is 44.01. And so the grams that we have of carbon dioxide, 1.668 grams of CO2. Now let's use the conversion factor, the density that they gave us for CO2. Flip it upside down, and the density is 1.830 grams per liter of CO2. So punching that in, we get that the volume of CO2 we have is 0.911 liters. All right, so now finally all we have to do is add together these two volumes to get the change in volume. Remember the volume to begin with of the system was 0 because all the reactants were solids, okay? And so delta V is 0.303 plus 0.911, and I hope that's right. My mental math okay there? Yeah, okay. So liters. And so the work done, remember, is minus P delta V. And so the pressure they gave us is 1 atmosphere. The change in volume is 1.214 liters. So the pressure volume work done with units of atmosphere liters is simply 1.214 atmosphere liters. Now, the problem is asking you for units, it's either joules or kilojoules. So you do need to have the conversion factor between liters, atmosphere, and kilojoules. That was on the previous page. There are 101.325 joules in 1 liter atmosphere. All right, so let's use that as a conversion factor. And by the way, another thing I point out about Smartwork is sometimes, well, a lot of times, you'll work a problem and you'll think, hey, they didn't give me the specific heat capacity, or they didn't give me delta H I need. Look in the Smartwork questions. Usually it's in the upper right, I think. But someplace there'll be a little hyperlink you can click on. It'll take you directly to the book. Now, if you didn't buy the ebook, just look in the book. Hopefully you have an O copy, or ask somebody what the constants are that you need for the problem, because a lot of times they don't rewrite them in the question for the problem itself. All right, so we had liters atmosphere work was 1.214. Okay, and we're going to go ahead and multiply those out. 1.214 times 101.325. So this work in units of, and I haven't rounded it for Sig Figs yet, so you want to get in the habit of carrying next the digits to the very, very end of any multiple step calculation. All right, so that's joules. If I want to convert that to kilojoules, it would be 0.12301 kilojoules. Now, Sig Figs matter in this unit. So let's go back and look at all the numbers they gave us and see if we can determine how many Sig Figs. So they gave us 2.55. That had 3 Sig Figs. Let's see, did anything else limit it? Let's see, densities each have 4 Sig Figs, and I think that's all the given information. Well, here we go. Atmosphere had 3. So, through all our multiplying and dividing, the factor with the least number of Sig Figs is 3. So your answer should be reported with 3 Sig Figs, which means that work done, and I dropped my negative sign. Shame on me. See, it's so easy to do. The pressure or the volume of the system is increasing, which means it's doing work on the environment, on the surroundings, so we need to keep that negative sign. So final answer for this one should be minus 0.123 kilojoules. Phew. Alrighty, that is it.